Hi everyone, and welcome back to another AP Calculus video. In this video we're going to be practicing a technique for integration called U-substitution, and this is part 2 of a 2-video series on U-substitution. And here in this video we'll be kind of discussing some of the tougher problems and really getting into applying U-substitution to really integrate and kind of hit at some tougher problems. We're also going to discuss how U-substitution can help us evaluate the indefinite integral as well as, the definite integral as well as the indefinite integral. So let's take a look. So let's start with one that's maybe a little less crazy. Remember, we talked about U-substitution as a technique to undo when things are multiplied. And in particular, if I have two things here that are multiplied together, like x squared, so these are the two parts, right? We have x squared and we have this. And what I'm going to look for is there a function inside of a function in one of those two pieces? And the answer is yes. We have the square root of a function. So the 5 plus 2x cubed is a function inside of another function. And so I'm going to let that be u in my u substitution. Now be careful, because just because two things are multiplied does not mean that U-substitution is the appropriate method of attack, if you will. There's another method that you learn in Calculus BC called integration by parts that also helps to undo things that are multiplied. But U-substitution should always be the first thing that we look for. And I know that I'm going to use U-substitution here for two reasons. Number one, I have a function inside my function. And number two, when I define that as my u, and then I find du, whatever I have left, so I have this square root, whatever's left, and here I'll highlight it in green, I have x squared dx. If that shows up when I find du, then I know I'm on the right track. So that's kind of a little self-check, and we'll be talking about that every time we attack a problem using U-substitution. We identify what u should be. It's always the stuff inside of another function. And then when we find du, the derivative of that inner function, part of that, in particular the x, the variables with dx, should show up in the integral. So highlighted in green, they show up. We don't care about constants, because constants, as we saw in part 1, we can divide out and we can move it around, and constants are easy to play around with. So what I'm going to do is divide by 6 and make this 1/6 du. And we have x squared dx. And now I'm going to replace x squared and dx in the original integral with what it's equivalent to in my du expression. So now I'm ready to kind of attack this and actually find my integral. So I'm going to rewrite it as u to the 1/2 power. And then the x squared and the dx I'm going to replace with 1/6 du. And we saw that we can move that constant out to the front. You're always invited to jump ahead to this step. You need to show some middle ground, identifying what u is and all that good stuff. But for the most part, there are lots of steps that I will show that you may not necessarily need to show on your paper, and that's just fine. But now I'm ready to integrate. So 1/6 u to the 3/2 divided by 3/2. And we learn we need to tack on that plus c. And if we keep on going, we're going to have 1/6 times 2/3, flip that bottom fraction, u to the 3/2 plus c. And when I replace u with its equivalent, we should have, let's see, 6 times 3, that's 2/18. So I'm going to write this as 1/9, 5 plus 2x cubed to the 3/2 power plus c. There it is. That's the answer that I should be getting when I solve a little problem like this. So let's keep going. Let's see a few more examples and see how U-substitution can help us through it. All right, so here we have cosine of 2x dx. And again, when I'm trying to figure out what u should be, now I do know the antiderivative of cosine is sine, but because I have the function inside of the function, I have to take that into account. So I'm going to let u be 2x. It's the stuff inside the cosine function. So du is going to be 2 dx. And dx is the only thing left after I do my u substitution. I'll have cosine of u. So I need to get that constant over here to this side. 1/2 du equals dx. And that's what I'll be replacing dx with. So when I rewrite this, I get the cosine of u du. I'm going to go ahead and jump to putting that 1/2 to the outside of my integral, just because I know it's going to go there eventually. And when I integrate, I get 1/2 times the sine of u plus c. Replacing u, I get sine of 2x plus c. Always replace u. There's the answer that I'm looking for. So let's keep going. And at any point when we approach a problem, you're always invited to pause the video and try it on your own. And if you get stuck, then, unpause and watch it all the way through. Now for this one, before you try pausing it and doing it on your own, I'm going to point you in a certain direction here, and then I'll let you pause if you'd like. But for this, the integral of tangent of x dx, remember, pst won't help you here. Pst only works when we're finding the derivative of tangent, or when we're finding the derivative of secant. So here, it's not as easy as you might think, like, oh, that's just from my formula sheet. It's secant squared. No, that's the derivative. So always be careful and consider which direction you're going with your derivatives and antiderivatives. But here, what I'm going to do is I'm going to rewrite this using sine of x over cosine of x. And then I'm going to let you decide what you want u to be. So if you want to pause the video and try it on your own, and if you try it one way and it doesn't work, then try it the other way. Try the other piece. It's either going to be sine or cosine. So figure out which one it is, and pause the video if you want to keep going. Otherwise, if you're still with me, here's how I'm going to think about what u is. If I let u be cosine, right, then du is going to be negative sine of x. Okay? And that's okay with me, because look, if I let u be cosine, then I have 1 over u, and then I have sine of x and dx that are going to be left. So u is going to become cosine, or cosine is going to become u. So whatever's left has to show up when I do that derivative, and it does. Now, if I went the other way, if I said, well, what if I let u be the sine? Then du would be cosine of x dx. The problem with that is when I go to do my u-substitution, I have u on here, and I end up dividing by, I end up with this problem because cosine of x technically is in the bottom. So I still have this cosine of x dx, and I would need to replace 1 over cosine. So this u-substitution is not the same when I try to replace it. So one way will work and one way will not. So you have to really pay attention to what's happening in your problem, because if u-substitution doesn't work in a situation like this, it's not as obvious, it's not as clear. What should you let it be? But when we let u be the cosine, the thing in the bottom, we're going to remember that this is a function. 1 over u is a function with an antiderivative that we should know and love, and that's natural log. So I'm going to think of that as my function in my function. And recognizing what's happening here is something that will take time. It's not something that you'll automatically be able to do, and you're going to mess up, and you're going to pick the wrong thing, and it's going to lead you down a rabbit trail, and you're going to be like, oh, now I got to erase and throw out my paper and start over. And that's going to happen, and that's part of the learning process, and it's okay. The greatest minds in history threw away more things than they published, I'm sure. So let's proceed with letting u be the cosine of x. So this allows me to have negative du is going to be sine of x dx. I'm going to move the negative sign over. So this allows me to have 1 over u times negative du. So I'm going to put the negative in front. And the integral here is going to be negative natural log of the absolute value of u plus c. Well, the absolute value, or u, is just, what did we say, cosine of x plus c. Boom, there's my answer. So we have to be willing to try something, recognize whether it's going to work or not, and then be willing to try something else. So knowing what we just did with tangent and using the identity of tangent being sine over cosine, I would invite you to pause the video at this point and use a similar identity here for cotangent, knowing that cotangent is cosine of 7x over sine of 7x. And remember, whoops, dx. 1 over u is a function that you can use. So when in doubt, go back to what we did with the tangent and see if you can apply that here. Go ahead and pause the video, give it a try. And if you're with me or coming back from pausing the video, here's how we're going to approach this. I'm going to let u be the denominator. That means du is going to be cosine of 7x times 7 for the chain rule, dx. Now, the 7 is okay. I can move that over to the other side, which I'm going to. I'm almost always going to move the constant to the other side. And I like this because, and I'll use a highlighter here, if u is 7x, then whatever's left needs to be replaced when I find u. So here's what's left. So I got that by itself, and I'm going to replace that green amorphous blob up there with 1/7 du. And so here's what it looks like. I'm going to do the integral of 1 over u times 1/7 du, 1/7, 1 over u, du. So that's going to be 1/7 times the natural log of the absolute value of u plus c. So we just have to remember what u was. Always record, by the way, anytime you do a u substitution, you have to record it. The AP grader has to be able to follow your line of thinking. So always write every little thing down. So here we go. Natural log of the absolute value of sine of 7x plus c. Wrap it up in parentheses. Always a good thing to do. So there's my solution. That's how I evaluate that integral. So let's keep going. Let's see some more tricky problems. All right, so here we have a problem, the integral of 1 over cosine squared. Now, I'm going to remember that 1 over cosine squared, I'm just going to rewrite this integral. This is what this is. So when I try to figure out what is going on with this, this is kind of tricky, but 1 over cosine, kind of reminds me of something. And I'm going to remember that I can use trig identities here to simplify this. Now, this turns into secant squared 2x, which should look familiar because the derivative of tangent is secant squared. So here, when I do my u substitution, sometimes if I notice I have 1 over cosine or 1 over sine, changing it to those secants and cosecants is helpful to me in this process because of that relationship of finding the antiderivatives and the business with secants, tangents, cosecants, and cotangents. So here I'm going to let u be the 2x, which means du is 2 dx. I'm going to move the constant over, 1/2 du equals dx. So now, when I do my u substitution, I'm going to have secant squared u times 1/2 du. I'm going to move the 1/2 to the outside. And the antiderivative of secant squared is just tangent. So it's 1/2 tangent of u plus c. I'm going to replace u, 1/2 tangent of 2x plus c. And there's my answer. So sometimes manipulating our trig functions and using trig identities is really helpful to us in solving these problems. So let's keep going. Ooh, this is a fun one. So I'm going to remember, just like sines and cosines, natural logs with that exponent, there's another way to do this. So I'm going to rewrite this again, and I'm going to group the natural log together and raise it to the 5th power through parentheses. Now, this is like one of those sine or cosine problems that we saw with our tangent or cotangent. When we have a fraction, we don't know what to make our u. And what I would recommend to you is anytime you have stuff raised to a power or stuff inside another function, start with the stuff. So here we have natural log to the 5th power. We'd want to start with natural log because it's stuff. It's a function being raised in another function, this power function. That's what the 5th power is. Also, if you ever are tempted to say, well, I'm going to let u be x, then du is dx. That doesn't get you anywhere. It just rewrites the integral with the letter u instead of the letter x. So it's not helpful in any way. Don't ever let u be x. It's just a dead end. Here I'm going to let u be the natural log of x, which means du, and this is going to be helpful, du is 1 over x dx. Now remember, when you have a fraction, you can rewrite fractions like this. You can say this is the natural log of x to the 5th power times 1 over x. So you can separate your fractions like this. The denominator just becomes 1 over whatever the denominator is, and you can turn it into multiplication. It's multiplication by the reciprocal, another way to think about it. And this is helpful to me because if I rewrite ln x as u to the 5th, so this is my u, whatever's left has to be replaced when I find du, and it is. So this is magical. This is amazing. I'm very happy about this. So I'm going to have u to the 5th power times du. Oh, that's not too bad. Okay, so that's u to the 6th over 6 plus c. Replace the u. That's the natural log of x to the 6th power over 6 plus c. Well, that's not so scary. There's my answer. That's not so bad. So you always have to pay attention to what's happening in your problem. You have to be willing to try different things for you, have them not work, and then go down another path. So let's keep going. Now we're going to apply what we've been doing here with U-substitution to the definite integral. And essentially what I want you to understand before we even begin is that it is the same for the definite integral as it is for the indefinite integral. We just have an extra step at the end of evaluating that antiderivative using our limits of integration. So let's walk through this, and I'm going to kind of show you two different approaches to using U-substitution with a definite integral. I'm going to show you approach number 1, which basically involves your numbers, right? This is the easiest way to go about it. So here we go. Tangent of x, secant squared. For my u substitution, I need to figure out what am I going to let u be and what am I going to let du be. Well, if I let u be secant squared, right, because or let u be secant, well, we can think of this as tangent of x and then secant of x squared, right? If u is secant, then du is secant tangent. And actually, oops, let's erase a little bit of this. There's more than one approach to this problem. But if we let u be secant of x, then du is secant tangent of x dx. And we end up with this situation. This is interesting because there's two ways to solve this and they're both right. If I replace one of the secants with u, then, remember this is tangent of x times secant of x times secant of x. So if I replace one of those with u, then the derivative is left, right? It's tangent secant. So this is really cool. So I'm going to evaluate, and I'm going to drop my limits of integration. Anytime I do this, u substitution for a definite integral, I'm going to drop my limits of integration. I'm not going to include them. And it's going to look like this, u du. It's really cool. So it's u squared over 2. I'm not going to worry about the plus c because it's a definite integral and it's just going to go away anyway. But then I'm going to rewrite it with secant in there. So secant squared x over 2. And now I'm going to go ahead and put my limits of integration in there. Now I'm not going to include it in this train of equal signs. I want to make sure that I'm not saying that two things are equal when they're not. Because I dropped my limits of integration here, I'm just finding the antiderivative. So now I'm going to jump back in and I'm going to go over here. I'll change colors so we can really separate it out. Secant squared x over 2, this is what I'm going to evaluate from 0 to pi over 3. Now why did I drop my limits of integration? Well, because I'm integrating something with u. Those numbers 0 to pi over 3 are for x. In order to put limits with a u expression, I'd have to go find different limits because we're evaluating the u function from a value of u to another value of u. 0 and pi over 3 are x numbers, so we have to not use them when we have u's in the problem. So until we go back to using x, we need to make sure that we're not including those limits. And if you're just doing this as a side work, even on a free response, as long as it's clear that it's your workspace, you can have this kind of two different trains of thought. Just be careful about using equal signs. Don't be too liberal with them. So now I'm going to come back over here, and we're going to evaluate this antiderivative. Secant squared at pi over 3 over 2 minus secant squared at 0. Secant's 1 over cosine, so even if I don't have a calculator, I can figure this out. Pi over 3 is 60 degrees. Cosine of 60 degrees is 1/2. Flip it, it's 2. 2 squared is 4. So we have 4 over 2, and then this will be 1 over 2. That's going to give me 3/2. Now, that's if I let u be equal to secant. What if I chose u to be a different one, a different value in this problem? I would argue that it would produce the same result. So let's see how it plays out. So this time, I'm going to let u be the tangent, which means du is secant squared. That's handy. So that means that I'm going to be evaluating the same exact integral. u du, which means it's going to be u squared over 2. Notice I don't have my limits of integration here, and that's on purpose, which is going to be tangent squared x over 2 evaluated from 0 to pi over 3, which when we plug these in, we should get the same exact answer. We're going to have tangent squared of pi over 3 over 2 minus tangent squared of 0. Now tangent of 0 is just 0, so that's nice. But then pi over 3 is 60 degrees. The tangent there is square root of 3. So square root of 3 squared, oh, that's going to give me 3/2. So it didn't matter which one I let u be equal to u here. Both of them worked, and they both worked really well. So occasionally you'll have a situation where it just kind of works out, and that's kind of nice. Now remember, the key here is that when you're doing a u-substitution involving x, you should not include those limits of integration anytime you have an expression involving the letter u. It's only when we get the antiderivative back with the letter x that we should put those limits back in. Be really careful about any equal signs that you use, because you will lose credit by setting two things equal to each other that are not in fact equal. It's called a linkage error. So let's keep moving on. Let's do this really tricky one here. And we're going to evaluate this using limits of integration. We're going to go from 0 to 1. And so we're going to talk about what do we recognize as being x, or sorry, what do we recognize as being our u? And here the denominator is the bigger function. That would be another indicator. Because remember, if we wanted to let u be x, then du would just be dx. And we'd be rewriting this whole equation with the letter u instead of the letter x, and it will have gotten us nowhere. So we're not going to be doing that. What I am going to do is I'm going to say, well, here I'm going to let u be the x squared minus 4. I like to let it be the bigger function because when I do the derivative, usually that replaces the smaller function of x. And in this case, it will. Du is just going to be 2x dx. So I'm going to move my constant over, and there's my x dx. Oops. So remember, the goal is if I let this be u, then whatever's left, the x dx, I want to be able to replace that with something involving du, and I've been able to do that here. So let's go ahead and proceed. So now I'm going to evaluate this integral, 1 over u du. Notice no limits of integration. I'm getting rid of them. So this becomes the natural log of u. Okay, and then I'm going to replace the x. So x squared minus 4. And this is what I am going to evaluate from 0 to 1. So, oh, and I forgot my 1/2. I knew I felt like I was forgetting something. 1/2. There we go. So now I'm going to just plug my numbers in. I'm going to have 1/2. And then when I plug in 1, I'm going to have the natural log of -3, the absolute value though, minus, when I plug in 0, I'll have -4. Those are going to turn positive. And I'm going to remember there's some great properties of logarithms that I need to start familiarizing myself with just to make it a little bit easier for myself down the line. I'm going to drop the absolute value bars, make those numbers positive. So I'm going to have 1/2 times the natural log of 3 minus the natural log of 4. When I have two logs that are being subtracted and they have the same base, like natural log has the base of e here, I can turn that into division of one logarithm of a quotient. And so it's going to look like this: 1/2 times the natural log of 3 over 4. This is a rule that I will have, and it will come back around quite often, and in particular in Calc BC. This is a skill that we need. It happens a lot in some of the integrals that we're going to see later on. But getting familiar with this is really important because on an AP exam, the multiple choice questions will always be fully simplified, and you need to be familiar with those rules of logarithms to be able to simplify to select the right answer on a multiple choice exam. Now I have one last question to end out our video lesson here with, and that is what happens when I do want to get the proper u values for my limits of integration. So this is a sample multiple choice question that one might find on an AP exam. And if we're using this u substitution that's given, and we have this integral, which integral using u substitution is it equivalent to? Well, the first thing I'm going to do is I'm going to say, well, let's write what we have. So if u is 3x, then du is 3dx. I'm going to have 1/3 du equals dx. So I know my integral is going to have a 1/3 in it. So I can almost throw out d immediately because there's no 1/3 there. So I'm going to go ahead and do that. So now I've narrowed my choices down, and best guess, I have a 30% chance of getting it right, 33%. So now I'm going to go ahead and continue with my u substitution. So I'm going to have u squared and then 1/3 du. Okay, so I'm on the right track. So it has to be one of these three, okay? Now, we'll look at the difference between each one. They're exactly the same except for the limits of integration. And I've already told you that the x numbers up here, this 3 and this 1, they go with the variable x. So anytime you replace x with a u substitution, those limits will be different. So I can almost go in and cancel out the one that has the same limits because the 1 and the 3 will not be the same. What will they be, though? Well, anytime that I do this u substitution, my limits turn into functions of u. So here, where I had 1 to 3, my lower limit will become u of 1. My upper limit will become u of 3. Basically, I need to take the limits that I started with and plug them into my u function. So u of 1 is going to be 3 times 1. U of 3, oops, and it's 3x minus 1. Silly me. Is going to be 3 times 3 minus 1. So that's going to be 2, and that's going to be 8. Oh, those are my new limits. So right here, that allows me to go here and choose option B. My new limits are the u values at my old limits, 1 and 3. So my actual answer will look like this. And as a matter of fact, if we go back and look at any of the problems that we had where we did not plug in the limits up here, if we had replaced any of them, and let's see if I can zoom out enough, here we use this one, we would have replaced them with u of 0 and u of 1, and then it would have been proper. And if we wanted to evaluate, instead of plugging things back in, instead of plugging the x equation in and using the original x limits, which by the way I think is the easiest and most straightforward, you can actually create a shortcut where if you find what u of 1 and u of 0 are, so like in this case, u of 1 would be what I get when I plug them into the u equation. So I'd have 1 minus 4, that'd be negative 3. U of 0 would be negative 4. If I took and evaluated this function here with u in it, and I used negative 3 and negative 4, I would get the same answer as I ended with. And here, just to prove it to you, I'll show you, it would turn into this. It would be 1/2, and we'll go ahead and put our box. We'll say from negative 4 to negative 3. you'd have the natural log of the absolute value of -3 minus 1/2 times the natural log at -4. That should look familiar. When you do the absolute values, you end up getting the same result, 1/2 times the natural log of +3/4, which is exactly what we got when we replaced it. So there is a shortcut around it. You just have to really understand what you're doing with your limits of integration and be really careful and understand that when you have a function involving u inside your integral, if that's your integrand, then you need to have limits involving u. You need to find the limits for the u function. If you just want to bypass all that and do the U-substitution and get to the part where you get to put x back in, well, then you just stick with the original limits of integration. I think that's easier. Not everyone will agree with me, and that's fine. It's not about saying there's only one right way. It's about finding the most efficient way and the way that you understand and can be successful with. So with that being said, keep in mind that U-substitution is a tricky business, and it's not always going to be something that you're going to be successful with first time around. Keep at it. The more you practice, the more types of problems you see, the more challenges you face and overcome, the more likely it is that you are going to be able to find success consistently and frequently. So keep at it, and just always remember, you can do this. You've got this.